I'm Jonas, and I'll be talking about graph coloring in the context of algebraic proof complexity. And this is joint work with Susanna de Rezende, Jakob Nordström, Shuo and Kilian Risse. They're all also here. So we're going to be talking about the graph coloring problem. We have a graph G. We want to determine whether its vertices can be colored with K colors so that there is no monochromatic edge. One of the original 21 NP-complete problems. You've all heard of this problem before. Let's do a very small toy example, just to be overly certain that we know what problem we're talking about. So this small 4-vertex graph can be colored with three colors, but not two. So coloring seems to be a very hard algorithmic problem. There are strong theoretical results even about the hardness of approximating coloring. And the best algorithm that runs in polynomial time that we know about colors a K-colorable graph with something like K times n over polylog n colors in the worst case, which is almost it's close to the trivial n. And even if we know that the graph is 3-colorable in advance, then an algorithm that finds a coloring for this graph will use something like n to the slightly less than 1/5 colors in the worst case. And this is still quite a bit more than 3. And in general, it's NP hard to approximate the coloring within the factor n to the 1 minus epsilon. In practice, the situation is not as dire. There are multiple approaches that solve it quite well in practice. Some of these are backtracking search and integer programming. And another line of work is using algebraic algorithms for this purpose. And this is a celebrated series of works by Deloitte et al. And these algebraic algorithms are actually captured by these algebraic proof systems that we know and love. So besides a proof complexity lower bound for coloring being interesting in itself, I don't have to motivate this to this audience. I think we actually also get unconditional hardness for these algorithms by proving proof complexity lower bounds. So previously what was known for these algebraic proof systems were worst case exponential lower bounds for coloring. But the instances that are hard, they sort of come from reductions to other problems essentially. So it was consistent with our knowledge that coloring was actually easy for these proof systems, except in some few artificial cases. Of course, we don't think this is true, but we can rule this out using some kind of average case hardness result. And this was done previously for the resolution proof system by Beam, Culberson, Mitchell, and Moore, which also implied running time lower bounds on average for state-of-the-art set solvers, modulo caveats. And this is the main result that we achieve, that with probability 1 minus the law of 1, the polynomial calculus proof system will require exponential size for refuting that a randomly sampled graph is 3-colorable. And if you just tune the parameters, it will not be 3-colorable with high probability.
So
yes?
Maybe you're going to get into this and then you can skip this. But
sure.
When you say random graphs, what is the average degree of the graph for which this result holds?
So the chromatic number of a random graph with average degree, something like d, is like d over log d or something. So you have to pick d over log d so that it's larger than 3. Otherwise, the result is trivial because it's satisfiable.
Yes,
but something like that.
But you think like whatever that trade-off is, the result will hold.
Yeah, large enough. This will hold.
Large enough constant, yeah.
Yes. But again, like the lower bounds, the parameters in the lower bounds, of course, depend on which constant you choose. But and if it's constant average degree, the lower bound is very strong, measured by the number of vertices in the graph. So let's just introduce polynomial calculus formally. So again, most of you will have seen this before. Polynomial calculus is a proof system that proves that a set of polynomials has no common root. And the way it does this is just by deriving new polynomials in the ideal generated by the input through either linear combination or multiplication. And these are just the operations that the ideal is closed under. So because these operations preserve common roots, if you manage to derive a constant polynomial starting from the input, you will have proven that there couldn't be any common roots in the first case. And this is actually a sound and complete proof system for if you know in advance that your polynomial is going to take Boolean values. Otherwise, you need an algebraically closed field for this to be true. And the two complexity measures that we're interested in this talk are size, which is the total number of monomials in the proof lines, as well as degree, which is the largest degree that appears in some monomial in the proof lines. So to make polynomial calculus reason about the graph coloring problem, we want to encode it as a system of polynomials, and it looks like this. We're going to use Boolean variables, which indicate whether the vertex v gets color I or not. The first two lines of this system of equations essentially say that every vertex gets exactly one color. And it is important to have both of them if your field characteristic should divide the number of colors. And the third line says that there are no monochromatic edges. And again, finally, you have the Boolean axioms.
But this is not a CNF.
No, not really. The first line is not a CNF, but this is how you usually code it.
But it doesn't matter. I mean, we work for a CNF setting as well.
Yeah. And just to mention that the techniques that we use also deals with another encoding more common in math. In particular, it's used in these algebraic algorithms I mentioned, where instead of having Boolean variables, you're adding a kth root of unity to the field. And then you encode the variable, the vertex v getting color I as assigning the value xi to the I, to the corresponding variable.
It's simply by substitution, right?
Yeah. So more formally, the main result simply says that if G is a sparse random graph on n vertices, and again, here we have to choose the sparsity parameter so that it's unsatisfiable, but this is no problem. Then with probability 1 minus lid of 1, the polynomial calculus proof system requires exponential size in the number of vertices in the graph to refute that G is tree-colorable. This result holds over any field, and it holds both for random regular graphs and Erdős-Rényi graphs. And the way we prove it is by proving a linear degree lower bound, which by known results will imply an exponential size lower bound. So for the remainder of the talk, I'll try to sketch how you prove polynomial calculus degree lower bounds. So essentially, we're interested in the set of polynomials you can derive in degree at most d. And we want to, in particular, show that 1 is not a member of this set. But for most problems, this red set is rather opaque, and it's very hard to characterize what polynomials are in this set. You can do this for instance, the pigeonhole principle, but for coloring, it seems very difficult. So what we will do instead is to over-approximate it by something that we understand a bit better, but which still does not contain the constant polynomial. And the way we construct the over-approximating set is by using what's called OR operators. And this is an operator taking polynomials to polynomials, and it should have these 4 properties: that it maps all of the input polynomials to 0, and it should be linear. So in particular, it should map linear combinations of things that map to 0 also to 0. And it should map multiples of things that map to 0 also to 0, if the degree of the ingoing polynomials is not too large. And finally, it should map the constant polynomial 1 also to 1. Because then you could just take this over-approximating set to be the kernel of the operator and get a degree d lower bound. So why is it called an OR operator? One motivation for this could be that it's very closely related to the notion of reduction modulo ideals, modulo polynomial ideals. And we'll need some notions from here for the lower bound. So I'll just introduce the bare minimum on this slide. So in reduction modulo ideals, you have a total order on your monomials, and you want that 1 is the smallest monomial. Then for a given ideal, you can define what's called the reduction operator with regard to this ideal. It takes a polynomial to another polynomial, where the image of the operator is the polynomial with the smallest terms, such that you can write it as your original polynomial minus something in the ideal you're reducing by. it's sort of like the polynomial analog to the remainder term that you get to dividing two numbers. So I'll try to sketch why R operators are related to reduction modulo ideals. So if your set of input polynomials were satisfiable, then you could not derive the polynomial 1, and this is by soundness of the proof system. But if this were the case, then an R operator could just be reduction modulo the set of input polynomials, because certainly they are in the ideal that you're reducing by, so they're mapped to 0 by the operator. Not hard to see that the operator is linear. And by definition of an ideal, if something is in there, then a variable times that something is also in there. So then it satisfies this multiplicative property as well. But now there is no degree restriction at all. Finally, since you cannot derive a constant polynomial 1, and it is small, then it will actually be mapped to itself by the operator. So you can sort of think of an R operator as pretending to be reduction modulo ideals when you have an unsatisfiable input. And you want it to be constructed in a smart way, which makes it so that low degree computations cannot really tell the difference between actual reduction and your R operator. So again, this will be pretty important when we sketch the proof ideas. The properties we need from an R operator are satisfied by reduction, except for this thing where 1 should be mapped to 1. So could we sort of still leverage these properties of reduction when we actually define the operator? And Alec Novich and Rosborov tells us one approach how to do this, which is that you define the operator using real reduction, but then you reduce different monomials in a given polynomial modulo different satisfiable subsets of the input. This means that 1 will be mapped to 1 because we're always reducing by satisfiable stuff. And then we want to carefully choose which subsets we associate to each monomial so that the inconsistencies compared with reducing everything modulo the same thing are sort of invisible in low enough degree. So in a bit more detail, how we implement this in our paper is that each monomial gets associated, like the monomial is mentioning some vertices in the graph. It gets associated to some slightly larger set of vertices along with the ideal, which is just the k-coloring polynomials restricted to the subgraph whose vertex set is S of M set. And then we define the operator locally on each monomial, meaning that we apply reduction to each monomial separately, and then we sum up the result. And that's the result of the operator. So now I'm going to be a bit vague and a bit incorrect, motivating the technical property we're after from these S of M sets. So we want R to look like reduction modulo ideal for low degree polynomials. So maybe if we choose these S sets very well, so that they do most of what you can do with reduction modulo satisfiable subset of the input when you apply it to its monomial, then for some polynomial P, say it consists of two monomials, and by definition, R applied to P will be the sum of the reductions of the monomials modulo their respective sets. But maybe it doesn't matter if we actually reduce both modulo a larger set, namely the union of them. Maybe it's enough. You do everything you can with reduction, only with this S of MIs. Then applying R to this polynomial P will actually be reduction modulo an ideal, and you can hope that it has the nice properties we're after. So the technical property we want is that reducing a monomial modulo its ideal is the same as reducing it modulo a larger ideal, which is generated by a larger subset of vertices in the graph. Again, this is not quite the correct motivation for why you want this property. It gets a bit more technical than this, but it's a good guiding intuition to have. So this is a very syntactic condition as it is. it says you're saying that the best reduction of M by this ideal U, it could be done already in the smaller ideal S of M. But these ideals are talking about colorings on subgraphs of your graph, right? So it should have some more semantic meaning. And that semantic meaning is the following. It's not immediate that this is what results from it. But we're going to inherit some order on linear order on the vertices, because reduction is always done with regards to some ordering on the monomials. So this translates over to an order on the vertices of your graph. And the task is to be able to extend every coloring of this S of M set to one for the larger set U in some order preserving way. And again, this is very vague, but essentially what it says is that this larger set U, it doesn't really say anything more than S of M about the colorings of the vertices mentioned by the monomial, that is by assignments to the monomial itself. And what order preserving means in this context is that the colors outside of S of M should be either fixed in advance before you assign anything to S of M, or they should depend only on one single smaller vertex in S of M. So for instance, in the picture, you can see that we couldn't hope to fix the color of the vertex V1 before we assign anything to S of M, because it has an edge to S of M. So we would be, if we assign it to blue, we would be violating a coloring constraint by assigning S of M to blue. But this vertex V2, we probably shouldn't worry about. It doesn't have any edges to S of M. So we could hope that we can just fix it in advance.
So you're saying each color in U has depends on only one smaller.
Yes, exactly.
Okay.
Exactly. You start with the coloring on S of M. You want to extend it to the whole larger set U, and you want to so the colors in U, not in S of M, will depend on the colors in S of M in general, and but it has to depend on the colors in S of M in a very restricted way for this to work. And again, it requires some argument, an argument to show that this is what you end up with. So this is the goal, and we now want to identify the obstructions towards achieving this goal. So essentially, there are three such obstructions. The first one is that there is some vertex which depends on more than one vertex in S of M. And the second one, which is maybe a bit less obvious, is that if there is some dependence between neighbors of S of M in U, like in the picture here. This sort of indirectly constrains what you can assign inside S of M, so we cannot really deal with this situation either. And the third obstruction is if there is some neighbor of S of M which is just smaller than its neighbor, because then there is no hope that the color of that vertex will depend only on something smaller in S of M. So the idea is that we want to get rid of the obstructions, and we'll just do it in the most direct way, where we're going to start. We will construct this set S of M in an iterative way, where we start with S of M just being the vertices most relevant to the monomial, the vertices it mentions, as well as the descendants of the vertices that the monomial mentions. This gets rid of the small neighbors. And then while you see one of these bad structures, you're just going to add that bad structure as well as all of its descendants to our set S of M. So this maintains the invariant that there are no smaller neighbors, and eventually you will have gotten rid of all of the obstructions. The resulting set looks something like this. And now we're in a pretty good position to extend the coloring on S of M to the whole set U.
Sorry, I must have missed something. The graph is oriented.
Exactly. So you have an order on the vertices of the graph. So then this gives you an orientation of the edges. linear order on the vertices.
Yeah, I thought that all vertices in U are supposed to come after all vertices in SM in the ring.
Sorry, I didn't understand the question.
So I thought that before all vertices in U are after all vertices in SM, the ordering.
It just has to hold for their neighbors where there's an edge between them. Then they're smaller.
It was just intuition about that condition. It was just an intuitive. This is the precise condition.
I think he's defining S of M such a way that these conditions. That everything in U is after everything in S of M.
Everything that you points to S of M is a.
Yeah, exactly. Thank you. This just needs to hold if there is an edge between something in S of M and something in then the guy outside must be larger than the guy inside.
Yeah, I was just confused about the third type of obstruction.
The third type of obstruction.
Third.
Oh, the third, yes.
In general, you just start with any that like, you don't have control over the monomial, you don't have control over the neighborhood. We are in control of how we define the set S, and now we would like to define it in such a way that these things hold.
Yeah.
In general, if you just pick S in any which way, then there will be tons of violations. Now we're trying to fix this to get sort of a nice S so that the neighborhood U has this nice property.
Right. So if we manage to do this, we have sort of removed all of the obstructions in the simplest way. We've just added them into S of M. And then we pay with the worst lower bound, just by making the set S of M larger, but being able to accommodate the restrictions. So now we can extend the coloring on S of M to all of you by sort of fixing some good coloring outside of the neighborhood. Then you look at what you assign on S of M, and then you can sort of patch it on the neighborhood, essentially. But the problem with this is that we don't know that the size of the set we're constructing doesn't just blow up. It might just become the whole graph, in which case we're dealing with an unsatisfiable set of polynomials again in the ideal, and then we haven't really done anything. So we have to show that the size doesn't blow up too much. And the main ingredients that we use for this are first pseudo-random property, which is local sparsity, which is a property that it's not hard to show that random graphs have with very high probability. It's saying that every small subset of vertices has an induced subgraph. The induced subgraph has not that much more edges than there are vertices. If you're in a bounded degree graph, this is sort of dual to the notion of expansion. Like most edges are leaving the graph, is what expansion is saying. So that means that there cannot be that many edges inside of the small subgraph left. And the second property is a bit more technical and also something a bit less standard. It's a very good choice of this vertex ordering. And this was introduced by a paper by Romero and Tunchel from 2022. And the intuition is that we're always adding all of the descendants of every vertex that we include in S of M. So to have any hope of bounding the size, we really need this set to be very small for every vertex. And one way to make sure of this is that there are no long ordered paths in the graph. Like if they all have length some c, and then the max degree in the graph is not large, it's some delta, the size of the set of descendants of a vertex is something like delta to the c. And random graphs will have some vertices with large degree, but there are so few of them that you can sort of ignore them, or you can add them to S of M with and not pay that much. So the key idea is that you should order the vertices by a proper coloring of the graph, because then the ordered paths will have length most the chromatic number of the graph, which is very small in random graphs. Because of course, if two vertices are in the same color class, there's no edge between them. So An ordered path has to switch colors at every iteration, at every step of it. So now just a proof by picture that SVM doesn't grow too much is that at every step we're adding at least one more edge than vertices to SVM. And because there are short ordered paths, we're only adding a few vertices per step. So you're increasing the density of the graph at each iteration. But this cannot go on for too long because the graph is sparse. So this means that there is only a bounded number of iterations. Now for some open problems, where the first one is, of course, will be very interesting to see average case lower bounds for coloring proved for other proof systems as well, perhaps being informed by some of the techniques here. Maybe the most natural candidates are Shirley-Adams, sum of squares, cutting planes. It's been very well-known open problems especially for this semi-algebraic systems. And another more technical remark is that these results that we obtain through this method, if you generalize the method, it's sort of not taking the field characteristic into account at all. And there are other lower bounds where you have some sort of characteristic dependent criterion for hardness, for instance, the work of Aleknovich and Rozborov. And maybe you can sort of refine the techniques in this paper to also include something like this. So summing up, polynomial calculus will require exponential size for covering a random graphs. And it actually implies exponential running time for some algebraic algorithms that are successful in practice. And some future directions are to refine the techniques to account for characteristics and as well as coloring lower bounds for other systems. Thanks.
Have some questions.
At some point you claim that this works for Fourier and Boolean encodings, right?
Yeah.
But this is the degree lower bound.
Yes, exactly.
The size works for both, or?
So there is no size degree relation for the Fourier encoding, but these algebraic algorithms are essentially solving a system of linear equations where the number of variables you're solving over depends on the degree of a Nordström's refutation of coloring. So you're solving a it's like n to the of the variables.
But if the algorithm is like more clever in deciding which monomials,
right?
you could do it with polynomial. I mean, probably not, but
yeah,
it's not
perhaps,
excluded.
yeah, that's a valid valid point that there is, yeah, the degree lower bound works. But
I mean, several of these algorithms we're talking about basically degree 4 Nordström lower, as good algorithms, and so this is like hugely ruling out that class of algorithms.
Yeah, but some they do some processing as well, right?
Not anything really significant.
Okay, let's time.
Yes.